Okay, so I start with the main updates of version 2. So the first update is that we can now download the Fermilab data directly from the graphical interface. So what you need to do is just put the name of the source here or the coordinates, put the energy range, which is preset by easyfermi, but you can change it if you want, and set the time window that you want. Then you just click on these buttons here and download the data. Another improvement here in the configuration is that now we can set up a configuration file that allows you to do an improved resolution analysis. So by improved resolution, this means that if you check this box, we will only select the best PSF photons in Fermi. So we are selecting only PSF 2 and 3 photons, which are the 50% best direction reconstructed photons. You can also improve the sensitivity of the telescope. And if any of you here have ever done a Fermi analysis, if you start at 100 MeV and go, let's say, up to 300 giga-electron volts, you do a zenith cut angle at 90 degrees. It's the standard. However, this is very makes you lose a lot of photons in high energies. So ideally, we should have a zenith angle for each energy band, and that's what that's what happens in easyfermi if you check this box here. So we slice the data set in energy intervals, and for each energy interval, we give a different zenith angle cut. So at the end, we have a higher sensitivity at higher energies. The improvement in sensitivity is not that much, is around 4%. However, if you want it, you can improve it. At the cost that the analysis will take much longer to run. You can also combine both, so you can have a high resolution and high sensitivity analysis. And another new feature is that for the light curve now, we allow for adaptive beaming light curve. This is not the traditional adaptive beaming light curve that maybe some of you are familiar with. This is a method exclusive from easyfermi, and the advantage of this method, if compared with the previous adaptive beaming light curve algorithm, is that we can do it in parallel. The previous, the one that is published in the literature, we cannot do it in parallel. It's impossible. Not impossible, but very hard to make it run in parallel. This is an example of an adaptive beaming light curve for the Blazer OP313. So this is for the last 6 months. We have these quite large beams in the beginning, and then when we have the flare, the beams get much smaller. So this allows us to extract much more information from the light curve. Oops. Okay. Another new feature of easyfermi is the SCD box. We already did the SCDs in version 1.0. However, in version 2.0, we have a lot of improvements in this section. So we now allow for EBL correction. So if you are analyzing the gamma ray spectrum of a Blazer that is at redshift 1, let's say, you put the redshift here. You choose here one of the EBL models that can be Saldana Lopez, Dominguez, Finke. There are 5. And easyfermi, using gamma pi in the background, will correct the gamma ray spectrum for EBL. And we also perform a Markov chain Monte Carlo estimation of parameters. So we have 5 possible models for that. And we allow the user to add VHE data, and this for you, especially that do science with Cherenkov telescopes, is very important, because you can do in a single fit Fermilat and MAGIC or LST analysis together. So if you add a table here that I will show you how this table looks like in the next slides. If you add this very high energy table here, easyfermi will fit the spectrum in the joint data. This is an example of the spectrum of Markarian 421. I'm actually using fake very high energy data here. I took real high energy data and I just shaped it a little bit because I want to use this same presentation for another conference. And okay, this is the Fermi data for Markarian for 2 months. And this is the magic, was the magic CTA, the magic LST data that I shaped it a bit. So you can see that the fit is performed in both data sets. And here we have as comparison the fit from FermiPy. You can see here that these semi-transparent points are the original, the observed data points. So, and the dark points are the points corrected by EBL. Okay, all of this information is saved and you can access it by yourself. This is a standard plot done by easyfermi, but all the data is saved in case you want to do your own plots. Okay, so let's go to the tutorial. Now I'm going to the beginning of easyfermi. This is the tutorial of installation. I'm not spending a lot of time here because it's just copying and pasting. If you use Windows, you may have to install this extra thing here, the libgl one. And to run easyfermi, you just do Python C import easyfermi, or you set it as an environment variable, like for instance in your .bashrc file, and you can simply call it easyfermi from the terminal. And okay, how to use easyfermi? This red box here contains is selecting everything you need to know to use it. So to analyze a source with Fermi, you need to know the name of the source or the coordinates. You need to know the energy range that you want. However, this is preset by easyfermi, so you can change it, but this is the typical range that we use for analysis. And you have to choose the time interval. This interval, this time here, is the second when Fermi started collecting data. And so you cannot go before that. It's impossible here in Fermi, it does not allow you. And you also need to know if your target is listed in this catalog here. In this case, it's for FGL, data release 3, but we have data release 2, for FGL, normal for FGL, and 3 FGL. So if your target is listed in this catalog, yeah, you have to know. So if it's listed, yes. If it's not listed, you put no here and you give a name to this target. It can be any name. That's it. That's what you need to know to analyze Fermi-Lat data. With this information, you can download the data files. So you click here to download the photon files, here to download the spacecraft file, and here to download the diffuse emission files. However, the diffuse emission files, you only need to download once. I put it here because maybe you don't know where to find it, but you only need to download it once. Once you have it in your computer, you just click in these 3 dots here and you can find it. It will save some time. Okay, so you set up what you want to do, you download the data, and here you select what you want as data products. So would you like light curve, adaptive binning light curve, SCD? Would you like to correct it for EBL? You would like to measure if this source has extension? And would you like to relocalize the gamma ray position, the gamma ray center of the source in the sky? And if you want to compute a TS and the residues TS for the source. And if you are using a Linux or Windows, you press go and that's it. You just have some patience because it takes a long time to run. But that's it. If you are using Mac, it may work, may not work. It depends on the Mac. you press go and cross your fingers. Okay, so, okay, this is the tutorial of easyfermi. This slide, the tutorial for installation, and this is the tutorial for using. That's it. All of the other slides, I'm just giving you some extra information and show you how things work behind the scenes. But these two slides are the tutorial. Okay, so the fit. We do a bind analysis with FermiPy for fitting all the sources in the region of interest. And the standard optimizer is new minuit. If you want, you can come here, check this box and change the optimizer. But the standard one is minuit. If the fit of the ROI do not converge, easyfermi deletes all of the sources in the ROI that have TS below 25 and perform the fit again. Except if your target has a TS below 25. In this case, easyfermi deletes all the sources with TS below the TS of your target before continuing for the fit. This typically solves any problem that you have with the fit, but if it doesn't, you can come here and customize a little bit the fit. So you can change the model of your target. Here, for instance, if you put Markarian 41, easyfermi will select automatically the model for Markarian 41 that is in this catalog here, and we'll do the analysis with that. But if it's not converging, you can change the model here. Here you have all the models available for FermiPy, which is power law 2, log parabola, several power law exponential cutoffs. You can also manually delete some sources from the ROI before the beginning of the analysis. And you can normalize the galactic emission model, the isotropic model, freeze the shape of the target. You can play a lot with the fit. But all of this is, you typically don't have to touch. If you want, you can do it. But typically you don't have to do anything.
Okay, so instead of deleting all the sources, could be something that can be changed. So delete the sources below TS of 9 or below TS of 4. Or 25 is a pretty big TS. If you're removing many sources that might actually be contributing to that.
Actually, this is fixed in easyfermi. So if the fit does not converge, then everything below 25 will be removed. I just released this, but this is a good point. Maybe TS 16 would be better. Yeah, but this is just a consensus, right?
You can like a free parameter, you can say remove sources beyond TS X, and people can select X to be 9.
Yes. I see. Yes, I can. Yes, I have some space here. I can maybe squish this and put an option for a TS limit. So,
instead of deleting, instead of squeezing, and instead of is it possible to just squeeze everything?
Yes, it's definitely possible to do that. But I don't think it's a good idea because first you run one fit, and then you discover that it's not okay. These parameters are saved in the analysis. So if you freeze it and run again, then you freeze these parameters in the wrong way. So the standard procedure in the Fermi-Lab collaboration is delete. But yes, this will be a possibility. In easyfermi, no. But you can do that, but in easyfermi, with FermiPy, for instance, but in easyfermi.
And yeah, 15.
15. More than enough. Okay, we do a lot of diagnostic plots with easyfermi, but most of them are the standard diagnostic plots that we have with FermiPy. This is a new thing that I have with easyfermi, and people typically don't use this kind of plot, although I think it's very, very important. This is the angular separation between your target and the sun, here along 3.5 years, more or less. I did this plot for the unidentified gamma ray source, LASO, this number here, which is a extragalactic unidentified source of LASO. And you can see that over 3 years, the sun is quite far from this target. However, if you are working with, let's say, with a light curve, and this distance crossed this line, which means that it's closer than 15 degrees from the sun, then the sun may affect your observations. So these diagnostic plots can help you a lot, especially if you are dealing with light curves, but also with SCDs. These are the other diagnostic plots that we do. Actually, do much more, but I just threw some of them there. These are all Fermi Pi stuff, so I did nothing here basically. These are just automatic output from Fermi Pi. And this is how the Markov chain Monte Carlo works. So we try to maximize this likelihood function, where this is the data point, the differential flux data point. This is the error associated with this point, and this is the model that the spectral model that we are adopting. So the spectral models are 5. So we have a power law, a log parabola, this log parabola 2, which is a very convenient parametrization of the log parabola, where we have where the fit gives us directly the energy peak and the energy flux at this peak, and the curvature, of course. And we have 2 power laws with exponential cutoff. One is this one you are seeing here, and the other one is the same thing, but with B set to 1. This is only for the Markov chain Monte Carlo. And the posterior distributions of the Markov chain Monte Carlo are all saved in the scd.fits file that is saved here in this output directory. Yeah. Okay, this is the same plot I showed you before. So the very high energy data is automatically included in the fit, as you can see here. All of these data points are saved in this file called target, the target name underline scd.fits. So you have access to the observed light curve and also the corrected light curve, as well as the best fit and the posterior distributions. So, okay, so how does the very high energy table looks like? It's a normal table, it's a standard table from Gamma Pi. So it looks like that. Probably most of you already are familiar with a table of this kind. And actually it can be any fits table where the first extension of HDU have these columns. That's just what matters. The EBL absorption models, we are using these 5 absorption models, and we are using the Gamma Pi class EBL absorption with alpha normalization set to 1. And here, easyfermi is basically not doing anything special. It's just importing Gamma Pi, and Gamma Pi is doing the hard work. Okay, how the adaptive binning works. With easyfermi, we first compute the standard, the constant binning light curve, and then we do a loop where we go inside each bin, and if the TS of this bin is above the TS threshold that we set in the graphical interface, is above twice that value, then this bin will be splitted in n new bins. So let's say that the threshold value you put in the graphical interface is 50. If the TS of this point here is 100, it will be split in 2. If it's 150, it will be split in 3. Okay, and at the end, this is a light curve for BLAC during the high state between 2019 and 2024. And here we have these beams that change following the activity of this target. And we see that the general shape still looks something somewhat similar, but we have much more information in the adaptive binning light curve. Of course, we can simply do this light curve with a higher resolution. However, you lose a lot of time with doing that because and you can run very easily in upper limits. This is a very useful feature of easyfermi. Let's suppose you did your analysis 3 months ago and you have to dedicate to another project, and then you come back to your analysis and you don't remember what you did. So you just click here, menu, load the GUI state, and it will print here, it will recover all the information that you had and the last time you did the analysis. So it's very useful. Another option of easyfermi is doing a customized analysis. So for instance, easyfermi allows you to do extended source analysis, but with only 2 models, a disk and a 2D Gaussian. However, let's say that you have your own extended model and you want to include it in the likelihood as a fixed file. You can manually add it to the configuration file and then upload it here. And many other things. You can play a lot with the customized mode. If you are lost at some point with easyfermi, you can just scroll over a button and a tooltip will appear. For instance, we cannot see my mouse here because when I take a print screen, the mouse disappears. But my mouse was over here, and then it says, okay, check this box to slightly improve sensitivity, It gives you some information about what the button was. I'm over. And okay, if you are curious about how easyfermi works, you can take a look at read the docs. We are still updating it. I released the easyfermi 2.0 2 weeks ago. So I'm still working on the documentation, but we already have more than that. Feel free to go there. We have some tutorials on YouTube. However, these tutorials are for the version 1.0. I'm going to upload several new tutorial videos. Actually, if you downloaded this presentation, you can click here to go to the documentation and click here to go to the YouTube channel. You can visit, you can download and install it in GitHub. If easyfermi is useful for you, give us a star there, GitHub. And this is the easyfermi community, but this map is a bit, I know that it's, I'm not accounting for everybody. These are only the people that contacted me about easyfermi. So we have people from the States, Brazil, Spain, Italy, Germany, China, India.
Russia.
Yeah, Croatia is tagged here. Yeah. But if you use easyfermi and you would like to be included in this spot, you can just you can fill up this form. It's available in GitHub as well. So you just click there. We have four questions for you, and you can help us to make these statistics. And to acknowledge easyfermi on your publications, you can cite this paper here. And since we use FermiPy, GammaPy, AstroPy, and EMCE, it would be nice if you cited also these other papers. The team of easyfermi would like to acknowledge also Ilaria Viale that works here in Padova, and Elisa Vicentin, who is there, because they tested a lot easyfermi. Elisa especially on Linux, and Ilaria in the Mac. Ilaria is the reason that I know that the analysis can work in a MacBook. And Michele Perezano, which is another author, is the reason that I know that in other Macs it doesn't work. Yeah. Okay, my last slide will be an advertisement. So I spoke about easyfermi a lot, but this year, stay tuned for EasySpec. I had to do a lot of optical spectroscopy during my PhD and a little bit in the postdoc. And I had to use IREF a lot. Maybe some of you here had to use IREF. And IREF, I never liked it actually. And I started developing this, last year this tool called that I call easyspec that does everything for long slit optical spectroscopy. Optical, but it can be near infrared and near ultraviolet as well. So since the image reduction, like a bias, master flat, cosmic ray removal, up to tracing the spectrum, calibrating by wavelength in flux, correcting for atmospheric and dust extinction, and the line fitting with Markov chain Monte Carlo. So stay tuned for easyspec that it's coming out this year. And that's it. The summary of easyfermi 2.0 is that you can download the data directly from the graphical interface. We offer you the option of doing a higher resolution and higher sensitivity analysis. We can do constant and adaptive binning light curves. We have this very useful plot, diagnostic plot, giving the angular separation between the target and the sun. We estimate the parameters with Markov chain Monte Carlo, the spectral parameters. We can do EBL corrections with 5 EBL models. We accept very high energy data as an input. It's very easy to recover in your past analysis, just go in the menu and load the state. And stay tuned for easyspec. That's it.